So we are to our last section of chapter 9, and I'm sorry, I hope you guys can hear me as well as possible. I have just enough congestion that it's making it a little hard for me to talk. So surfactants is my last section. And this is what we call surface active chemicals. And these examples of these would be soaps and detergents. Those are your major surfactants. And what happens, the actual molecule itself latches onto the microbe or the contaminant and will circle around it and hold it. And very effective. Soap molecules are hydrophobic, and the other end is hydrophilic. So therefore, soap can be attached to a particle, oily deposits, things of that nature, and then also to water. And then therefore, we have things that can draw away oily substances and dirt and things of that nature from materials to reduce contaminants, microbes, because they tend to harbor in those regions. So that's very effective as well. We also have what's called quats. Now, quats are quaternary ammonium compounds. They're composed of an ammonium cation. Hydrogen atoms will also be replaced there so they can actually attach and bind. They're colorless, tasteless, harmless. So they're great for a lot of medical applications. Zephyrin, let me give you some brand names. Zephyrin is one of them. It's benzalkonium chloride. Cepacol is also another brand name that will have quats in it. Quats will disrupt cellular membranes. They are also bactericidal, fungicidal, and virucidal. Our next one is heavy metals. These are your high density metals: arsenic, silver, copper, mercury, zinc, the problems with a lot of these metals is that they will build up in the body over time and they can be toxic. So this can be quite dangerous. We know from experience of previous years, arsenic containing compounds were common even in the medical field when we first started with a lot of medications 150 years ago. And we have now hence learned that arsenic is toxic and builds up in the body and cause serious issues. So we don't tend to use that one. However, it is very effective at being able to kill bacteria. They are low-level bacteriostatic and fungistatic agents, so they reduce the numbers quite well. Let's talk about silver for a minute. Silver is most commonly used in creams for burn cases, and also eye drops for if a child has gonorrhea in their eyes to prevent blindness. They'll use silver nitrate because whenever babies are born, if they pass through the birth canal and the female has gonorrhea, then that is going to pass through to the baby at that point in time, and the risk of it getting in their eyes is high. Silver is has great antimicrobial properties. Silver bandaging, they use that sometimes laced in the bandaging. I don't know if some of you have actually got to work with that with wound care. I learned a lot from one of my home health nurses a couple semesters ago or a semester ago that was talking to me about these uses for silver that we use in bandaging and so forth, as well as we have zinc bandaging too. That just kind of help with reducing the numbers of microbes in a wound. When we're dealing with dressing wounds and things of that nature, it's very important to be able to reduce those numbers. So dressings, burn creams, catheters, things of that nature, we may use silver. I've also heard of silver being used in surgeries, surgical prep and things of that nature. I can't remember exactly who it was. I had a student that said they used a silver sponge in a surgery that they had to reduce the actual microbes that were present. So it's very interesting to see what we use silver for as far as that goes. Copper is good to reduce algae growth in reservoirs. Copper is used a lot in agricultural commodities to reduce the number of algae. So the pond scum and green that you see in a swimming pool, they'll also use a copper compound to be able to reduce that. So it's really good at doing that. Copper, zinc, mercury as well is used to control mildew in some types of paints. Let me see. I talked about silver, talked about copper. Mercury. Mercury used to be used a lot in various medicinal purposes, such as mercurochrome. Your grandparents may have called it monkey's blood. Now we know that mercury can build up in the body and is toxic, so we don't want to use that specifically for that. Mercury has been used, remember the thimerosal, in vaccines. However, most things that we use nowadays for vaccines are thimerosal free for the most part. If you are using a vaccine that is not thimerosal free, they will typically give you a waiver that you have to sign that gives you acknowledgement that yes, you do know and understand you are using a vaccine that has mercury in it. Our next group is aldehydes. Aldehydes are typically gases for the most part, but they are basic compounds that will be things such as glutaraldehyde, formaldehyde, formaldehyde can be a gas. Glutaraldehyde is used a lot to kill bacteria, viruses, and fungus in a reduced solution. It's fairly expensive, however, it's fairly effective. Formaldehyde is much cheaper, but it's very much so an irritant and can cause a lot of problems. When we dissolve formaldehyde in water, that is formalin. And that's what a lot of your morticians and healthcare workers may use. It's used for embalming and to disinfect hospital rooms. instruments in a hospital as well as machinery. We have to be very, very careful because it is a carcinogen. Okay, it's carcinogenic, so therefore it can cause cancer. It's also very much so an irritant. We used to use formalin for creating for preserving dissection specimens. However, nowadays we use something that's much less severe. Trust me, that stuff stunk so bad. It was absolutely horrible. But we have come up with a much safer usage material. It's called CaraSafe, which is a very, very much so diluted version of formalin. One little thing that's interesting about formalin is that people have been taking this. We have to, now it's considered, I can't think of the words that I'm looking for, but we have to distribute it out, and we have to know who has what amount, because people have taken formalin and they're using it illegally to create a form of heroin that's actually very dangerous and very, very unsafe. And they're also lacing it with a number of other illegal substances, and it's causing deaths. So, I guess they get what they wanted out of it, but it's causing a lot of death. It's very dangerous. So now we have it basically to where you have to make sure you are distributing it out in an appropriate manner, and it's accounted for by the government. Gaseous agents is our next one. So gaseous agents, let me make sure I get all these down here. Ethylene oxide. And then we have propylene oxide. Those are the main ones I wanted to look at. Specifically ethylene oxide, that's used a whole lot. It's used in gaseous sterilization agents in hospitals and dental offices. We use this one a lot. Even NASA uses it to gas the spacecraft and things of that nature. It's used a whole lot to sterilize instruments that are sensitive to heat and things of that nature. The problem that we have with these gases, even though they're very effective, is that they're highly explosive, poisonous, and we have to be very careful. And some of them are even potentially carcinogenic. Now, your next one is enzymes. I don't really ever talk too much about enzymes. However, the cool thing about enzymes is that we use them to naturally biodegrade a lot of other materials. So those are really cool and great. Antimicrobial drugs, I'm going to talk to you guys about that whenever we get into the next chapter, which is antimicrobials, chapter 10. All right, so let's talk about some of the ways we evaluate these chemical agents. One of which is what we call the phenol coefficient. Now, I'm talking about these. They start on page 281. And the phenol coefficient is a great way to compare all of our chemicals to our very first phenol, our very first, antimicrobial chemical agent that we used, which was Joseph Lister's phenol that he originally used, a carbolic acid spray. So this we compare to everything else as far as its effectiveness. So for example, each and every disinfectant and antiseptic is given a number that is going to indicate whether or not it is more effective or less effective than phenol. A number greater than 1 denotes more effective. A number less than 1 denotes less effective. So, for example, chloramine has a coefficient of 133 when used against Staph aureus. Now, and I'm pretty sure I misspelled that. Hold on. A-U-R. Yeah, that's where it is. I'm really not with it today, guys. E-U-S. I'm like, oh, that didn't look right. Okay, when used against Staph aureus. Now, if you use it against something else, okay, so let's say chloramine, again, it's only going to have a phenol coefficient of 100 against, I'll just put S, so I'll write it all up, Salmonella enterica. The difference is that with each microbe, it's going to have a different efficiency. So therefore, each microbe it works against, we are going to have a different coefficient. Hopefully that makes sense to you. The used dilution test that's on here, we do need to understand that. Basically, your used dilution test, we didn't get to do this one, and I'm not going to do that for your labs. Your used dilution test is pretty neat. Okay, so it's going to tell us how effective different antiseptics may be. So you'll basically take your metal cylinders, dump them down into a solution of bacteria, your bacteria broth that's been growing bacteria, pull them out, and then you'll put them into the disinfectant. When you do this, you can evaluate how effective your disinfectant is over a period of time compared to each other. So it's a used dilution test. The one I really like the best is going to be your in-use test. So basically what you do here is you take a swab from the actual object itself. So you can swab your shoe or whatever you may want to do, okay, both before and after the application of a disinfectant or an antiseptic. Then you grow it and culture it. And then you do one after you apply the disinfectant or antiseptic to your shoe or whatever. And then you grow and culture it. This is going to see how effective that actual disinfectant or antiseptic was in that situation. So you can actually see whether or not it works. That is called the in-use test. In-use test. We're not going to look at the Kelsey-Sykes capacity test at all. Also, there is another chart for this chapter. Let me go ahead and pull it up here. It is table 9.5, chemical methods of microbial control. And this also shows a list of antimicrobials. And this went through all the method, action, level activity, and some uses that we have for them. So that will kind of shorten a lot of the information that we have here. This is on page 281 of your textbook. Hopefully this will be helpful and help you with understanding a lot of the material that's here. This ends my chapter 9 lecture, and we will be going into chapter 10, which is actual antibiotics, which will be quite extensive.